in kinetic theory of gases, remember in kinetic theory of gases, the important thing was that they looked at gases from a statistical physics point of view. All right? And they came up with this final equation. PV equals 3/2 N K average. All right?
Isn't it 2/3?
2/3.
Yeah, it's right there.
Oh, I'm sorry. Thank you. Thank you, thank you, thank you. 2/3. 3/2 comes about in a second. That was my fault. Okay, this was the number of molecules. And this is the average kinetic energy. Okay? Average kinetic energy and the number of molecules. All right. Now, this looks strikingly familiar to what they got from experimentation, which is nRT on the right-hand side. Okay? PV equals nRT, universal gas law. PV equals 2/3 N K average. All right? So I think we did this last time, right? We set these equal. 2/3 N average kinetic energy equals nRT. Okay, two different N's, number of molecules and number of moles, right? Okay, we're going to rearrange this and solve this for the average kinetic energy. Okay, so average kinetic energy equals 3/2, there's my 3/2, and then I get N over N, and then I get RT. Got it? All right, number of molecules, number of moles divided by number of molecules. What does that give you?
Constant.
Very good, it gives you a constant. What constant is that? Yeah, it gives you Avogadro's number, right? This is Avogadro's number, so we're going to rewrite that. 3/2 N Avogadro RT. Is that the way you write that in chemistry as well? Avogadro's number? How do you list it?
Yeah, we write it in.
Do you write it in every time?
Yeah.
I don't know.
Okay, we're going to make a new constant. Because we have a constant here, we have a constant here. And so we're going to add or multiply those two together, and we're going to end up with this one. Okay, and this is the way you will normally see it in physics. Okay, where K sub B is a new constant, it's just Avogadro's number times, oh wait a minute, I got something messed up. This is not right. Number of moles divided by number of molecules is 1 over Avogadro's number. Right?
Yeah.
We had that backwards, or inverted. So change that in your notes, please. Mess that up. Yeah, because the number of moles is the number of molecules. Yeah. Okay, number of moles equals number of molecules divided by Avogadro's number, right? All right, so when I divide this over here, the number of moles, number of molecules, 1 over Avogadro's number. Do it again. Okay? All right, we got it?
Yeah.
So here's our equation. Boltzmann's constant is just another constant. No big deal. It's on your constant sheet. So everybody get your constant sheet out. Find it so you know where it's at. So that you don't have to memorize it. You just need to know what it is. It turns out to be about 1.38 e to the negative 23rd joules per Kelvin. Okay, it's just a constant, no big deal. Just know where to locate it on your constant sheet so that when it shows up, you can find it. All right. Now this tells us a couple of things that you might not expect. And we talked about this last time real briefly. is that all of the energy in a gas is due to the kinetic energy. Okay? And that kinetic energy of the gas, why again is there only kinetic energy in a gas?
Because it's always in motion.
Well, one, because it's always in motion. That's true. Because if it stopped being in motion, it would be at absolute zero, right? But why no potential energy in a gas?
Because it's floating around. It's never moving. No. It's not being.
Why is there potential energy in a liquid and a solid, but not in a gas?
Where would you drop it?
It's not gravitational potential energy. Now remember, we're not talking about potential energy like gravitational potential energy. How do you get potential energy in a solid and a liquid?
Through the bonds.
It's the bond energy, right? It's the energy of the bonds being stretched or compressed, right?
So there is no one.
That's just it. In a gas, there is no bonding between the gas molecules. Now, as you go farther and farther in science, you'll find that an ideal gas works really great for something we call a monatomic gas, which means a gas. What's monatomic mean? You remember from chemistry? Yeah, just one atom by itself, right? So hydrogen is a monatomic gas. Helium is a monatomic gas. Oxygen, they mostly bond with each other, right? So you have a diatomic gas, correct? Okay. Or water vapor is not monatomic. And in water vapor, you have the molecules, while they're not bonded to other molecules, the molecule of water can vibrate. Okay? And so you end up with, it doesn't exactly act like an ideal gas. Okay? So, but if it does act like an ideal gas, which is at low enough temperatures, all right, or if it's monatomic, then all of the energy in the gas will simply be kinetic, and that's it. And what's crazy about this is when they went through this, they found out that that is a direct measure of the temperature, or the temperature is a direct measure of the average kinetic energy. So, a thermometer. When you take a thermometer and stick it in something, it measures the temperature. The temperature is a measure of the average kinetic energy for the gas. Now, wait a minute. This brings up something really important.
Oh, so if they ask us, what is something that we can heat up and stick a thermometer in, and the answer?
Sure. Sure.
I don't know how to check it.
Now, okay, if I told you that, let's make something up so that maybe it'll make sense. The average kinetic energy of the gas tells you something about the gas, but in most cases, in energy, when we're talking about energy and work, we don't care about what the average energy is. We want to know what the energy is, right? We don't care about the average. Like for instance, if I told you the average amount of money in this class was $10, would that tell you, that tells you something, right? But that doesn't tell you how much total money we have, right?
Well, if you know the people in the class, it does.
So how do we find out the total amount of energy in the gas then? You need to know how many particles you have, right? And you need to multiply by how many you got, right? Okay, so if we take this average kinetic energy, and if we take both sides and we multiply by the number of particles we have, or the number of gas molecules or atoms that we have, then we would know the total energy of the system, right?
Yes.
All right, so you could either multiply by the total number of molecules, N, or you could, if you know the number of moles, you'd multiply by the number of moles in Avogadro's number. Okay? So you multiply both sides by either N, but N equals the number of moles by Avogadro's number. Okay? And when you do that, you'll get the total energy of the gas. And that's going to equal 3/2 KB N times Avogadro's number times T. All right, but magically, guess what that turns out to be?
1.
3 halves.
That'd be awesome.
What's that? That turns out to be R. N, R, T. We get our NRT back. Party. And this turns out to be, unfortunately, everyone, they use the capital letter U, which doesn't make any sense whatsoever, but that's what they use. This is the total energy of the gas. All right?
Maybe it's because of the U you made right now.
That's the way.
Another U.
Oh, no. It has nothing to do with that. It looks like potential energy, but it's not. So the total energy of the gas is equal to 3 halves nRT. Now that ends up going to be really important for us later, okay? So what important equations have we learned from gas laws? PV equals nRT. And remember, we have two types of problems in gas laws. We have
Single state
single state
and change of state.
and change in state. Okay? One of those two types of problems. That's it. And then we've learned that the average kinetic energy equals 3 halves Boltzmann's constant times T. We've learned that the total energy of the gas is equal to 3 halves nRT. Okay? One last thing before we go on and leave gases behind. Okay? We'll actually work a few problems and then leave gases behind. Okay. If I've got a container, here's my container, full of a gas, but this gas has hydrogen in it and it has carbon dioxide. Hydrogen and carbon dioxide. And I heat the container up. So they're mixed in this container. All right? If it all has one same temperature, say the temperature is 600 degrees Kelvin. Okay? Does the hydrogen and the carbon dioxide have the same average kinetic energy? Yes or no? Yes. Because they have the same temperature. Boltzmann's constant's the same. 3 halves is the same. So they have the same average kinetic energy. Okay, now, do both the gases have the same average velocity? Or average speed, I should say, because their velocity averages out to be 0. Do they have the same average speed?
No.
Probably not, but why not?
Different size of the plant.
Because this is equal to 1/2 mv squared, right?
Yes.
Do they have the same mass?
No.
So they can't have the same velocity. So which molecules are moving faster? Which atoms, which gas is moving faster on average? Yeah, the one with the lowest mass must have the highest velocity. Okay? By the way, this is why Jupiter and Saturn and the other outer planets, the big gas giants, why they have so much hydrogen and helium and are gas giants, and Earth is not. The Earth has enough gravity to hold larger molecules of gas to itself, but not hydrogen. Okay? And I don't think helium either, if I remember correctly. Because what happens is in the upper atmosphere, at the temperature of the gas in the upper atmosphere, when the sun hits it, it warms up. And at that altitude, gravity's not enough to keep these things from flying away. Okay? That's why the Earth has a oxygen, nitrogen, carbon dioxide, argon type of atmosphere, and not a lot of hydrogen in it, or helium, okay? Because it escapes. It flies away on average, okay? Now, if the Earth was bigger, then the hydrogen wouldn't be able to fly away. Its temperature would not be great enough to give it a velocity that's high enough for it to escape, okay? So that's why the Earth will never turn into something like Jupiter or Saturn, okay? It can't. All right. In fact, that's also why on Mars, Mars's atmosphere is more carbon dioxide, because Mars is smaller than the Earth. And since Mars is smaller than the Earth, it has a hard time holding on to molecules like oxygen, okay? Even though it's colder, because they move fast enough for them to escape as well, okay? So, and that's also why the moon has nearly no atmosphere at all. Okay? Because the molecules, they get warmed up enough and they just fly away. Their escape velocity is too great for the moon to hold on to. Does that make sense? Why certain objects only have, will not have an atmosphere, like the moon doesn't have an atmosphere, but the Earth does. Okay? All right. Questions? Comments? You ready to solve a few problems to make sure you know how to do this? All right, because our e-homework is going to be kind of challenging. So let's make sure you know how to solve these. Oh, by the way, there are a couple equations for this. Let me write them down. I believe they're on your equation sheet. Find your equation sheet. Look in thermal physics. Your nice, glorious, hot pink equation sheet. And are they on there? Yes, they are. Let me write them exactly the way they're on your equation sheets. They look exactly the same. They look like this. They are VRMS equals 3RT over M equals 3KBT over mu. And these are square rooted. All right? Let me explain these to you. All right, do you see this over here? Where we said the average kinetic energy here equals this. Okay? If I move this 2 to the other side, right here, this 1/2 and this 1/2 cancels, right? Which accounts for our 3 in the equation, right? When I move the mass to the other side, you see that the mass goes to the denominator. So we have a mass down here, right? Mass and a mass in the denominator. Do you see that if I square root both sides? Square root, then I'll end up with V on the left and a square root on the right. Okay? So when I have 1/2 mv squared equals 3/2 kBt, the half goes away, the mass goes to the denominator, and I square root both sides. So I end up with a V equals 3kBt over m square root. Okay, but this m over here is written as a mu. Okay, mu means the mass of the individual molecule. Okay, so this mu equals mass of molecule. All right, so if this is mu, they just write it mu so you know which mass they're talking about. You can also rewrite this to be this. It is 3RT capital M, where capital M equals, I think that's molar mass, is that right? Yeah, it's molar mass.
Yes, you take my minute.
You're welcome. Molar mass from chemistry. So depending on which one of the masses you use, molar mass or mass of the individual molecule, you'll use either Boltzmann's constant or the universal gas constant, because remember, those are related by Avogadro's number, right? Okay. Okay, what do these tell you? These tell you the exact same things that we've already talked about. Is the average, it's like average velocity, gives you, depends on the temperature and the mass, right? Which we've already talked about. As the temperature goes up, the velocity of the molecules increases on average. If the mass of the molecules go up, the velocity of the molecules goes down on average. Now, this RMS, that means root mean squared. Who knows what that means? Anyone? Anyone? Root mean squared. Okay? Like for instance, root mean squared is a way to find an average of something that has an average of 0. So let me explain. The gas molecules in this room, on average, what's their
0.
velocity?
Oh. 50 million.
No, you had it right the first time. It's 0 because there's not a wind, right? Air's not blowing through here. Right? Yeah, now there is. If the AC would turn on, which it doesn't seem to be, then we would have wind, right? But if the air is just sitting here stagnant, then the average velocity is 0. But we know that the molecules are actually moving, right? They're just moving random. Some are moving this way, some are moving this way, some are moving that way, that way, that way, that way. Also, on average, they add up to 0, right? Okay, so a way to find an average of something that averages out to be 0, but even though they're moving, is to do this. Is you have, if you call this positive and if you call that negative, just make it easy. So if I have 10 meters per second that way and negative 10 meters per second that way. Yeah, the average velocity of these two particles, this one and this one, is 0. Okay, so the way they find an average for that, to give you a better idea of what kind of speed they have, okay, on average, not their velocity, but their speed, you square them both. What's negative 10 squared? 100. What's 100 squared? 100.
You said 100 squared equals 100.
Right.
That's 10,000.
10 squared equals 100. Okay, what if I square root them both now? Square root. 10, 10. Now we're assuming we take the positive, right? Okay, so what's the average now? Okay, the average now is 10, but the average is not the real average. It's an average of only the positives. Does that make sense? So you square it, and then you square root it, leaving only the positive. It's kind of a mathematical trick.
Just like average speeds to average.
Yeah, so essentially RMS is kind of like average speed, as opposed to average velocity. So if you see RMS, just think of it at this stage as average speed. Your math teacher may have issues with you calling it average speed because technically it's root mean squared, but it's like average speed.
Can't we just take one and negative?
So the average speed is 10. All right? So when we do this, the RMS velocity, or the average speed essentially, is this. Okay? That's a nice way to describe it. Very nice. All right. Okay, you ready to work a few problems? I'll take your silence as a yes. All right, here you go. Step number 1. You ready? All right, step number 1. In this particular problem, we're starting with a cylinder filled with 1 atmosphere of gas. The height of the cylinder is x. You compress the gas so that the new height is x over 4. But you do this real slow. You do it real slow so that the temperature stays the same. All right. I want to know, what's my new pressure in the gas? So what's pressure number 2? And that's the original pressure. Yeah, so the new one is x over 4. The new height. Yes, ma'am. Yes. Okay, first thing you need to decide, is it a single state problem or a change in state problem?
Single state.
Change.
You're not changing it.
We're not changing the state. This isn't changing the state. It means single state and changing state means you're changing the variable. In this case, volume.
Then it wouldn't be a problem if you weren't changing the variable.
You are changing the variable. That's why it's changing the state. A single state is just plug in
All great windows that overlook. All right, so is it a single state or a change in state problem? Is everything staying the same? No, then it's a change in state problem. So, what's your original state like? PV equals nRT. 1, 1, 1, 1, 1. Actually, that's always, right? State number 2, PV equals nRT. 2, 2, 2, and 2. What's staying the same?
The whole right side is staying the same.
Yeah, this is obviously the same, right? That one and that one is the same. That's staying the same. Are we losing any gas?
No.
Okay, so that's staying the same. So actually, you know what? I can just write those down once, right? Hey, so the whole right side's staying the same. So what does that make this kind of problem?
P1, V1 equals P2.
P1, V1 equals P2, V2. There you go. Now you've done all the hard part. The rest is just plugging in numbers. So what's my original pressure?
1 ATM.
1 ATM. What's my original volume?
No.
Ooh, X is not a volume.
What's the
Yeah, it's my area times X, right? So area times X is my original volume. P2.
This is your 1 ATM.
So what's my second volume? Yeah, it's area times X over 4. And look, my area cancels out, right? So what's my final pressure? 4 ATM. Nice. Piece of cake. Got it? All right. Okay, question number 2. Let's say you have a cylinder. Let's say it has a gas in it, and the gas is pressurized to 11 atmospheres. Its original temperature is 0 degrees Celsius. Okay? But this time, you add heat to it. Because you're not too bright, and you take it and you throw it into a fire. And you raise the temperature, so you add heat. And so afterwards, the cylinder looks like this, but now the temperature is 100 degrees Celsius. Okay, what's the new pressure? A lot. Well, the question is, will the pressure go up or down? How do you know it's going to go up?
Because the higher the temperature, the more pressure.
P equals nRT. And what's staying the same and what's changing?
Volume stays the same.
Same. So what's our equation become?
P over T equals
Yeah, P over T equals a constant, or P1 over T1 equals P2 over T2. Very good. So then once you do that, the rest is just math, right? Oh, somebody having math problems?
Yeah.
Why do we not have math problems?
Because we're not saying.
You can convert to Kelvin.
Ah, good. If they had put a different temperature than 0 right here, some of you may not have caught it the first time through. You need to be careful, because a lot of you caught it because I put 0 in here, and you put 0 down here and you go, oh, I'm dividing by 0, that gives me a problem. And saying, oh yeah, I can't have 0, so I have to convert it to Kelvin. But if I'd have put 10 here and 100, you just need to be careful. You always got to convert this to Kelvin, right? So you got to convert this 11 ATM over our temperature number 1 is 273 Kelvin equals our pressure 2 over 373 Kelvin, and you end up somewhere around 15 atmospheres, right? Excellent. All right. Let's say that this is 1 mole of gas. And that our volume here is 1 liter. Small L or big L for liters?
Big L.
Large.
Big L. 1 liter. Oh, you know what? That won't do. Back up. I mixed my problems up. All right, so tell me, what's the volume of that cylinder? If there's 1 mole of gas. Very good. Somebody said it. What is it? That's a single state problem. Because all we're doing this time is we're just picking one state or the other. It doesn't matter. Because the number of moles should be the same. And the volume should be the same. So PV equals nRT. You plug in the number of moles. You plug in the temperature. Convert it to Kelvin. Plug in the atmospheres. Uh-oh. We got a lot of conversions going on here, right? Okay, here's the issue with our e-homework tonight. Is that there's a lot of unit issues going on. So please be careful of your units. When you're dealing with PV equals nRT as a single state problem, you absolutely have to have this in pascals, meters cubed, mole, and Kelvin. Okay? Now they may ask for the answer in units of atmospheres.
I never do the units.
You must do the units.
It never marks it wrong for not having the units.
No, it's not plugging in.
No.
No, it's like when you convert
No,
it to
when, you must convert it when you do the math.
Oh, alright.
Okay? Now, if it's a change in state problem over here, you notice that I didn't convert atmospheres. Why am I okay not converting atmospheres over here, when over here I have to convert atmospheres?
What you just said.
They're the
I got
same.
lost in that.
Over here, I did not convert my atmospheres. But over here, I'm telling you, you got to. So why do I not have to here?
Because you're comparing it to ATM
Because I'm just comparing
to another
a ratio to another ratio, right? But over here, I'm using this constant, right? And that's the thing that gets you in trouble. Is when you use this constant, 8.314 joules per mole Kelvin, you have to have these units. Okay? All right. I don't really care what the answer is here. I just wanted you to realize that this is a single state problem when I asked that, right? All right. All right. What's my new temperature? I have a cylinder. I've compressed it over here. Here's the original pressure, final pressure, the original volume, the final volume. What's the new temperature? Assuming none of the gas escapes. Why is it the same?
Ratio.
PV equals nRT. Okay, that and that are staying the same, right?
Yeah.
And so what we have is P1 V1 over T1, or PV over T equals a constant, right?
Yes.
Okay? And the thing is that when we solve this, you notice that your pressure is doubled, but your volume is cut in half, right?
So it's all.
Yeah, so if you double the pressure but cut the volume in half, those cancel and these two have to be the same, right? Same as before. So you either say 10 degrees Celsius or what is it, 283? Okay, excellent. All right, now tell me this. Now that we know the temperature is 283 and it doesn't change. 283 Kelvin, and this is 283 Kelvin. All right, tell me, how many moles are there? Okay, is that change in state or single state? Single state, right? So all you got to do is just pick one or the other, because the number of moles are the same, right? It doesn't matter which one you pick. And you plug it in to find the number of moles. All right, how many moles?
85.
85 moles. Everybody agree with that?
Yes.
I will assume you're correct. How many molecules then?
5.12.
Yeah.
Key thing is I don't really care about the number. What I really care about is how do we get the number of molecules? Molecules equals moles times Avogadro's number, right? Which is, what's Avogadro's number?
6.022
Molecules per mole. By the way, if you don't remember Avogadro's number, I won't tell Dr. Tuttle. But it is on your constant sheet, right? All right, so just look it up if you get skunked and you don't remember. Okay, now, next thing is, we've done change in state problems then, and single state problems. Don't forget to be careful about your units. But now, let's look at this one. Okay, we've got a cylinder. I'm just going to look at it from the side. Here's our piston. All right, here's our gas inside here. And on top of here, I have a mass of 50 kilograms. Okay? The height here is unknown. The number of moles is 4. The temperature is 400 Kelvin. The area is 200 centimeters squared. Okay, I want you to find out what's the pressure inside the gas. Temperature is 400 Kelvin. Number of moles is 4. The height of the cylinder is unknown. The area of the top of the piston is 200 centimeters squared, and the mass sat on top is 50 kilograms. And I want to know what's the pressure. Very good. Danger, danger, danger. Convert. So let's convert this. What's that in meters squared? 2.
Meters squared.
I did. All right, here. 1 meter, 100 centimeters. That gives you 2. You are correct. But what units? Yoink, yoink. Leaves you with centimeter, meter. You only converted one of them. Yeah. Okay, now I do that on purpose because students do that mistake all the time. That's okay. We just need to make sure we don't do it again. All right, so if it's squared, you got to do this squared. You got to do it twice to give you meters squared. If you do it twice, then you get 0.02 meters squared. There you go. By the way, if you wrote down an answer of 2, but you put the proper units of centimeters times meters, technically you should get that correct. But I'll tell you, the grader probably won't spot it. So you probably want to put it in meters squared. Okay, but technically that's correct if you put the right units on it. Technically. All right, so. All right, there you go. You run into a problem here. How many of you are stuck? PV equals nRT. Is that a correct statement? Sure. And we know that, and we know that, and we know that, and we're looking for pressure, but unfortunately, volume is area times height. And we know that, we know that, we know that, we know that, but we don't know the height. So,
He said pressure is force over an area.
okay. All right. Now, this occurs a lot of times where what you've done right here, if you did all this, perfect. This is great. Unfortunately, it's just not going to get us where we want to go, right? So, we're happy with our genius, but we're sad that this doesn't get us our answer. So, it's time to back up, back the truck up, go down another road. And our other road is, hey, pressure equals force over area. So, what's our force? Well, our force is mg, and what's our area? Oh, we know. Pressure equals mg, which is 50 times 9.8 divided by 0.02 meters squared. Hey, look at that. We need that proper measurement here, or otherwise our answer's not going to end up in pascals, right?
All that other stuff is just extraneous information.
That's correct. Now, there's extraneous information. Now, I'll tell you what. You as students of this generation are better off at handling extraneous information than students from previous generations, because you've grown up in a generation of Google and Wikipedia and information overload. And you have grown up learning that there is lots and lots of stuff out there, but not all that is necessarily useful, right? Okay? Just remember those skills when you get to a problem. And just because the problem gives you all these numbers, that doesn't mean you have to use all these numbers, right? Some of it just may be stuff you don't need. That's all right. So by the way, when we do this, what do we get?
24,500.
24,500 what? Pascals. Uh-oh, I sense a problem.
Convert
No.
wrong units.
No.
Humans.
Humans? Whenever it asks for error, you don't ever say, no, not significant digits. That's not what I'm talking about. 24,500 pascals.
That's a lot.
Is it?
Yeah. Maybe.
No, not really.
What would consider to be average, roughly, pressure?
100,000.
Atmospheric pressure, 100,000. Whoa, 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 whoa. You're telling me the pressure inside here, with a mass on top, is less than atmospheric. Okay, this is time for you to use that little thing, that little voice in the back of your head that says, that doesn't make sense. Caution.
These questions don't always make sense.
We could be on a different planet, maybe. But if we're on a different planet, we have to use something other than 9.8. Drat. Okay, here's what we've missed. Here's what we've missed. All right, does everybody see that we've got mg, or the weight, pushing down on this? Now, we have assumed that this piston is massless. All right, I didn't give you the mass of it, so we'll assume it's massless. But is there anything else pushing down on it? Yeah, pressure from the atmosphere. Okay. Well, assuming we're on Earth, right?
I'm a Martian.
If we're on
Just
Martian
you look
world.
like one, dummy. You are one.
What do you got?
Oh, hi, hi.
Whoa!
Something I have
I sense sarcasm. The sarcasm meter just went off.
That was.
Careful, okay. Tone it down. Dial it down. Let's bring it on down.
You know Mr. Carter's rules, right? Don't let me see it and make it quick or something like that.
All right. 1 atmosphere. Okay. Everybody, we have weight on here, and unless it tells you that this thing is in a vacuum, you're going to have to assume that there's also an atmosphere pushing down. Now, is there an atmosphere pushing on the sides? Sure. But do we care about that?
We're assuming it's closed in.
Yeah, we're assuming it's closed in, so that won't matter, right? So only the pressure on the top is affecting the piston, giving it pressure inside, right?
Yeah.
Okay, so what do we have to do to fix this problem?
Add the 180.
So the pressure inside the gas will equal, here, let's just remember our forces from last year. If I've got this pushing down and this pushing down, then the pressure pushing up must be
Greater.
the same if it's going to stay in equilibrium, right? So it's going to be the pressure of the atmosphere plus the pressure from the mass. Now we've already calculated the pressure from the mass, right? So all we have to do is add 100,000 pascals. So we get 1, 2, 4, 500 pascals. See that? There you go. That's all you got to do. Just add the atmosphere on.
So that's the total.
So that would be the total. what we calculated was the pressure only because of the mass. So that's in addition to the atmosphere that's already there. Okay? Excellent. Now, I think I just helped you with most of your e-homework, but if you turn to e-homework problem number 2, take a look at it.
I don't have it.
You don't have it. Oh, should print them up early.
All right.
Okay, it says a bicycle pump contains air at STP.
STP, that's 1 HTP.
There you go. That's standard temperature and pressure. Okay? That would be 1 atmosphere.
0 degrees Celsius.
All right. The tire is pumped up. The volume of air decreases by, and mine says 63%, as you pump the pump. Okay, everybody?
Pump it up.
If this is an air pump, okay, with a little nozzle on the end. Here, look, look, look.
And you're running improvement.
I am. The wording says if the volume decrease is 63%. Whoa, whoa, whoa. Volume decrease is 63%.
No, decrease it by
So what's our new volume?
37.
There you go. So if volume 1 equals 100%, then volume 2 would equal, in my case, 37%. So our new volume is 37% of what we started with. So just be careful of the way that's worded. Okay? The wording is volume decrease. Okay? So you don't want the volume decrease. You just want to know what the new volume is. Right? There we go.
You know, Rudy, if there's
So
ever
your
a
volume
massive
decreases
junior suicide,
So
I know
in my
it's
problem, it was 63%. Yours will be a different number than mine. But when it says volume decrease, so if it says volume decrease of 90%, then your new volume is only 10% of the original. Just be careful of the wording. All right, everybody get out your thermo packet. Get out your what you absolutely have to know about thermodynamics to pass the AP Physics B test. All right, I passed that out last week. Those of you watching on video, print yours up. All right, thermodynamics. What were you doing? Disturbing my class? Passing through. Just passing through. Okay, thermo. Okay, let's make sure we get a couple definitions of thermo down before we get too far. Thermo. First of all of you, I want you to repeat after me. Ready? I will love thermo.
I will love Mr. Brewing.
No. I will love thermo.
I will love Thermo.
I'm not lying, really. I will love thermo.
I am not lying, really. I will love Thermo.
Now I say it with enthusiasm.
one thing's beating, but making us use enthusiasm, that's taking it too far.
All right. Now, thermo. Thermo is one of those subjects that a lot of students will kind of
Suck it.
do. All right. Yes. Actually, thermo is really pretty easy because thermo is just an extension of energy. And we incorporate gases and we make it do things for us. Okay? Thermo is the way that we, without thermo our cars wouldn't run. Without thermo, we mostly wouldn't have electricity. Thermo is one of the most useful concepts in all of science because it's really just an extension of conservation of energy. So it's useful in physics. You'll use it in chemistry, thermochemistry. It's useful in biology. It's useful in environmental science in a huge way. It's useful in astronomy. Okay? It is an all-encompassing idea. Now, when we first start thermo, we're going to start at a ground level. Okay, and it's going to seem somewhat vague at first, okay, but hang in there. All right? Because what we're doing is we're kind of stripping away all the extra stuff and just looking at some of the new things that thermo presents for us. And we're looking at it from a physics point of view. When you're in chemistry, you'll look at thermo from a chemistry point of view. Okay? How many of you already talked about thermochemistry in chemistry class? Yet? Have you done it yet? Okay, you will. All right? You will. Okay, so we have a couple of definitions. Definition number 1. A system. Okay? A system. A system is nothing more than a collection of stuff. Okay? It's a collection of stuff that you're going to keep track of.
Do you have to write notes? Like, what is on?
It's up to you. I'm just kind of going over what's in the packet. Okay? System is a collection of stuff that you're going to keep track of. The environment is everything that's not the system. Now, you can define your system to be anything you want. Like, for instance, we could define the system to be everything in this room, and therefore the environment would be everything in the hallway, above the ceiling, outside the walls, below the floor. We could also define the system to be all of the people in this room. So the environment would be the chairs and the air and everything else that's in this room but us. Okay, so you can define it any way you want. Most of the time in thermodynamics, our system is going to be a gas, and I'll explain why in a little bit. Okay, all the molecules in a gas that we're going to keep track of. Okay, next idea is thermal energy or internal energy. Thermal or internal energy. Now, we've already talked about this. Internal energy or thermal energy for a solid and a liquid consists of the kinetic plus the potential energy, kinetic energy, potential energy of each atom. Okay, the sum of all of that, all added up. Okay, so the sum of the entire thing. However, for a gas, if we're talking about a gas, it's just the sum of the kinetic energy. Because a gas, remember, has no potential energy. All right, at least in our ideal gas. Okay? This has units of joules, by the way. And unfortunately for us, the symbol, once again, is the capital letter U. Okay? All right, temperature. Let's make sure we understand what temperature is. Capital letter T is the symbol. Temperature is a measure of the average kinetic energy. We just got through talking about that, right?
Yes.
And for a gas only has kinetic energy. But for a liquid and a solid, the temperature does not measure anything that has to do with the potential energy inside the liquid or a solid. So temperature is an incomplete measure of the energy. It only gives you the average kinetic energy. And it tells you nothing about the potential. And it doesn't tell you anything about the total energy. So like in chemistry, you remember using Q equals mc delta T? Okay? This C, the specific heat, gives you an idea of what's going on with the potential energy. As the temperature changes, some objects have a lot of internal potential energy, and some do not. Like water has a huge specific heat, right? So it has a lot of energy stored in it for its temperature, whereas like a gas does not in general. Okay? All right. All right, so that's temperature. Temperature only measures average kinetic energy. We've got heat, Q. Heat is the transfer of thermal energy. Technically, heat means the transfer of thermal energy, so we shouldn't really say the heat flows from one object to another. Technically, we should just say the heat is, but in English it sounds better when we say heat flow. That's like, technically it's saying thermal energy flow, but we don't care. It sounds better.
Sahara Desert.
All right, this is in units of joules again. This is in units of Kelvin, by the way. All right? Okay, thermal equilibrium. All right, you ready? Objects that have the same temperature are in thermal equilibrium. Now, what does that mean? Okay, here, let's say we have object number 1.
Is that what we're talking about? We're talking about when we lay in the snow.
Yes,
We become the same.
that's correct. So like, yeah, if this object and this object are in thermal equilibrium, what can you tell me about them? There's no heat flow. Now, technically, there's heat flow both ways, but it adds up to be 0. Because like this one has molecules moving, right? This one has molecules moving. But they're moving at, on average, the same rate, right? Now, some of these are moving really fast, and some are moving slow inside. Some are moving fast, some are moving slow. So when I put them together, some of the fast ones here can hit some of the slow ones here and transfer heat this way. But some of the fast ones here will hit some of the slow ones moving here and transfer heat the other way. And that heat transfer is equal and opposite. So therefore, the net heat flow is 0. Okay? On average. So when things are in thermal equilibrium, they have the same average motion. So they have the same temperature. They'll have no heat flow. Okay? So here you go. You ready?
Yes.
Here's the 0th law of thermodynamics. That's correct, because they came up with the first law.
Before the 0.
Yes, before the 0th law. There's actually 4 laws of thermodynamics, and they came out in really weird order. And the 0th law came out after the first law. They didn't want to rename it, so they just called it the 0th law. The 0th law says this: if this object is in thermal equilibrium with this object, and this object is in thermal equilibrium with this object, then you can say that these two have the same temperature and they're in thermal equilibrium as well. Okay?
Wow, that is special.
I know. Actually, what happened, though, is when they were going through and studying all this stuff, they realized that if that wasn't true, they were really in trouble. So they went back and made sure it was true. Essentially, it means you can take the temperature of something, of this one and this one, and then they will have the same average kinetic energy. Right?
Sounds easy.
Yeah, it is easy enough. All right. So in thermal equilibrium, Q equals 0. That's really important. Okay? Q equals 0. All right, and our last thing is work, which is W, has units of joules. And we've already talked about work already. Work is the transfer of energy from one system to another. And remember that work equals F delta R cosine theta. F delta R cosine theta. But it's the transfer of energy from one place to another place. Okay? All right, now, let me go through real quick and show you where the first law of thermo comes from. You ready?
Yes.
All right, because we're going to do this one fast, all right? Okay, remember that work equals the change in energy of the system, right?
Yes.
That's technically E2 minus E1, right? Okay, that's technically kinetic plus gravitational plus spring plus electric plus however many others you have, 2 minus kinetic plus gravitational plus spring plus electrical plus however many other you have, 1. Okay? Because Because you could have any of those types of energies before and after, correct?
Yes.
Okay, so it just looks ugly when I write it all out. Okay, in thermodynamics we add two things. Those two things are, we add a different type of energy right here. That new type of energy we add is internal energy. Now, I know it looks kind of ugly and it's kind of confusing because we use U for potential energy and we use U for internal energy. But U with no subscript means the thermal energy, okay, of the object. So now we're incorporating what's going on inside the object itself. And that's new. That's change number one. Change number two is this, that we add a new way to change the energy of a system. And that new way to change the energy of a system is directly adding heat to it. So that's change number two. So let me put those in blue. Adding heat changes the energy, and now we're including the internal energy of the system. Those are the only two changes to what we've already studied in work and energy. Okay? Now, to make life as simple as possible when we study thermo, we will neglect all other forms of energy except internal energy, just so that we don't have to worry about them yet. Okay? So what we do is we say we're going to assume that these energies before and after aren't going to change much. Okay? That the kinetic before and after is about the same, that the gravitational and spring and electric potential energy before and after is about the same. So we're just going to ignore them. Now, is that a good assumption? Maybe, maybe not. But it's like when we assume that things are frictionless. In the real world, do we have things that are frictionless? Yeah, not really. But does it make the problem easier to look at and solve? Yeah. So what we're doing right now is we're going to neglect this just so we don't have to worry about it at the moment. Okay? When we do that, our equation becomes this. Q plus W equals the final internal energy minus the initial. And we usually write that this way. We write this as delta. So it comes out to be delta U, the change in internal energy of the system, equals Q plus W, and voila. We have the first law of thermo. The first law of thermo is almost the same as what we studied in work and energy. It just looks weird. Okay? But it's the same idea. But now we have two ways to change the energy of a system. You add heat directly to it or take heat away, or you can do work on it. Okay? So like for instance, remember when I said last time when I had a book or something? Here, I'm going to steal this. And I asked you if I was doing work, and I said, did I do work? And you say, oh yeah, you did, because you changed the potential energy. But now we've got things where I'm changing the energy of the system by doing work. Yeah, and adding heat to it. That's correct. So it's all the same idea as before. All right. So everybody, let's make sure we get our sign convention correct.
Make sure we get it away.
Oh, don't wipe it on my stuff.
I
might have germs.
I might have germs. I don't want to get sick.
That's right. I don't want to make myself sick. Okay, here we go. All right, here we go. Okay, this is my system. Yes, it's a sombrero system. It's just some random thing that I made up. I'm going to include everything inside there is going to be my system. Everything outside is going to be the environment.
It's an inside joke.
It's a Picasso. You're drawing. Oh, it's happy.
Sombrero has a face. That's scary.
Hey, at least it's not talking yet. All right, now, everybody, if I add heat to the system, Where does that heat have to come from? The environment. So if heat goes from the environment into the system, what happens to the energy of the system? It goes up. So therefore, we'll call heat going into the system positive because it makes the energy of the system go up. Okay?
Yes.
If heat leaves the system and goes into the environment, then the energy of the environment goes up at the expense of the system. And so the system's energy goes down. So therefore, we'll call heat leaving the system negative because that lowers the energy of the system. Does that make sense?
Yeah.
All right, now, that's pretty straightforward. Look for words like, if they said 1,000 joules of heat is added, is that positive or negative? Positive. If it says the engine runs and exhausts 500 joules of heat,
Negative.
it's negative. Okay, so anything going in is positive, anything coming out is negative. Piece of cake. Now, the harder of the two to spot is work. All right? Now, see if you get this. If the system does work on the environment, remember that work equals F delta R cosine theta. There must be a movement. All right? So if the system is going to move the environment, the system either has to move outward or move inward. Got that? The system either has to get bigger or smaller. All right. We need to talk about work real quick. Work. Okay, everybody, since work is F delta R cosine theta, it implies movement. So our environment and system have to move. If the system, if we're talking about their system, in order for it to move the environment, to interact with the environment, it has to move into the environment.
Isn't it already in the environment since everything around it is?
Everything around it is the environment. So for it to move the environment and to do work on the environment, it must move the environment. And the only way for it to do that is for it to expand or contract. So everybody, if our system expands and moves outward,
It pulls the environment outward. Or pushes it out.
So a balloon moves the environment.
yes. All right, now, if our if our system expands and moves out into the environment, is that positive or negative work? Now look,
It's positive.
is it applying a force to move the environment? Yes.
Yes.
Which way is the force?
Outward.
Outward. Which way is it moving the environment? Same direction. It's moving it in that same direction, right? So what's our cosine theta? Yeah, our cosine theta is 1 because they're in the same direction. It's moving and applying a force in the same direction, correct?
Yes.
Now, here's the problem. If the system does work on the environment, what happens to the energy of the system itself? It goes out into the environment, right?
Yes.
So what happens to, where did that energy come from? The system. So what happens to the energy of the system?
It decreases.
It has to decrease. Think about that. Think about that as we're waiting for lunch here, right? If you're working and you're lifting things and moving things around, you're doing work on them. But at what expense? Your energy, right?
You're not taking my energy.
Yeah, you're not taking my energy. All right, everybody. This is the confusing thing. Work done on
Energy.
the environment is considered negative work because it takes energy away from the system. Okay? But what if work is done... So wait a minute, this is reworded sometimes. This can also be worded as work done by the system. That's negative work, because if the system does work, it's going to lose its own energy. All right? But what if work is done on the system? Say the environment does work on the system.
Then the environment's giving the energy to the system.
Then the environment is transferring energy to the system, and the energy of the system will go up. So that's considered positive. Now, this will take a little while to soak in because it's a little bit counterintuitive, but here are the magic words you're looking for. Okay? Work done on the system. Is that positive or negative then? Positive, because the energy of the system will go up. Okay, what if the system expands? Okay, then it's expanding. That means it's doing work on the environment. Therefore, that would be losing energy, so the work is negative. Okay? What if the work done by the system? It's right there. It's negative. What about the system is compressed? Okay, if the system is compressed and the environment's doing work on the system. Okay, the whole thing is we're interested in when work is done, does the energy of the system go up or down, right? That's why we have those sign conventions. Does that make sense? All right, now, go. Everybody? Now, we talked about gases, gases, gases. And here's why we talked about gases. Actually, you tell me. Why is a gas unique and special and different than a liquid and a solid?
No potential.
It has no potential energy. That is true. And what is the thing that, since it has no potential energy, then the molecules aren't bound together, right? So the thing is that it can expand and contract. Now that is key. Look, if I take this marker, and I set something on top of it, and I heat the marker up, will the marker expand?
It'll melt.
Will the marker expand?
Yes.
Yeah. Will it then lift this?
Yeah.
Sure.
Just not significant enough.
How much work is done?
Negative.
Paquito. Little bit, right? Very small. Now wait a minute. What if I do that with a gas instead? What if I take a gas in a cylinder and I put something on top of it and I heat up the gas? The gas can expand a great deal. And since the gas can expand a great deal, can the gas do work?
A lot more.
A lot of work. And so that's the key thing, and why in thermodynamics we talk about gases all the time, because the gases allow us to do something that liquids and solids cannot do as well. It can physically do work for us. Because here's what we're doing, everybody, just so that you know. Here's our goal. Heat moves from hot to cold. It does this naturally. And what we want to do is, as this heat, Q, moves from hot to cold, that's energy. And we want to steal it. We want to steal that natural process and make it do something. And what we want it to make it do is work.
Make it productive.
And the thing that allows us to do that better than any other substance is a gas. Okay? Now, there are systems, thermodynamic systems, where they use liquids and solids, but we're going to talk about gaseous thermodynamic systems because that's the basis for all the others. All right? Time's up.